Sometimes when you have a sequence, you want to be able to find a formula for the nth partial sum instead of for the nth term. And when you do that, you're usually going to need to prove that, and induction is a good way to do that. So let's look at an example of how we would go about that. Let's say we have a sequence that looks like this. And we want to find the formula for the nth partial sum and then prove that. Well, remember, a sum is where we're adding up the terms. So the first partial sum of this is just the first term. And the second partial sum is the first term plus the second one. And the third would be the first and the second and the third terms added together. And the fourth would be the first all the way up to the fourth term, all added together, and so on and so forth. So these are all our partial sums. So what we need to know is there some kind of formula we can use to find the partial sum without having to go back and find all the terms and then add them all up? So let's look at this. Well, this is the first partial sum, and this is the second partial sum, and this is the third, and this is the fourth. And if we look at this, we can say, well, that's 1 times 1, and this is 2 times 3, and this is 3 times 5, and this is 4 times 7. And we notice that there's a pattern going here. We're taking the term number that we're going up to here and multiplying it times these successive odd numbers. So what we need to be able to do is make that into a formula. So we would take this and we would say, well, we've got our term number there in times, and then we need to figure out a way to write odd numbers in terms of n. So we know that if we do 2 times n, that gives us an even number, and if we do 2 times n for this one, we'll get 2, so that's 1 too many, and we do 2 times n, we get 4 here, and that's 1 too many. So we see that we're 1 too many every time, and so this will give us our proper odd numbers, and you can check this. You can say, well, okay, so I've got 1 times 1, that checks out. 2 times 4 minus 1 is 3, that works. 3 times 6 minus 1 is 5, that works, and so on. So what we have is what we're saying is this nth partial sum for this sequence. Now, the trick is we're going to have to prove this. So we need to use induction to prove this. So what we're going to say is we want to prove that this is true for all n, for every n integer. So we're going to use induction. So here's our statement that we're making that we want to prove. And so what do we start with? Right, we start with the anchor. We start by showing it's true for the first term. So is 1 equal to 1 times 2 times 1 minus 1? So 1 times 1, yes, the anchor is true. So you just write it out to show that the anchor is true. Then remember, you make your inductive hypothesis, which means we just rewrite it out with the k in there. So we're saying that this is true. That's our inductive hypothesis. And then we're going to prove that show that the next one happens. So what we do, remember, is we just add the next term. And remember, we're adding the same thing to both sides. So that gives us still an equivalent thing. So we just added the same thing to both sides. So then we have to simplify this right-hand side here. So we've got 2k squared minus k plus 4k plus 1, because we've got plus 4 and minus 3, so that's plus 1. So we have 2k squared plus 3k plus 1, which factors to be 2 times k plus 1 times k plus 1. So we need to look at this. We want it to look like this here. So for the k plus 1 term, for n equals k plus 1. So what we need to do is kind of rearrange a little bit. So we use our commutative property and flip that. And then we've got 2, and now we want to see if we can get 2 times k plus 1 to equal this. So we can say that this is the same thing as 2k plus 2 minus 1, because we want this minus 1 here. And if we have plus 1, that's plus 2 and minus 1. And then we factor out our common term there. And we have it. So then we say this is the statement for p of k plus 1. So p of n is true for every integer n by mathematical induction. So there you have it. So if we need to find the nth partial sum, the best way to do it is go ahead and write out several sums, the first 3 or 4, so that you can, until you see a pattern. Then come up with which equation is to show the pattern, and then you need to prove it by induction. Write out your anchor statement, show that that's true. Write out your inductive hypothesis and make sure you write that it is true. Then add your k plus 1 term to both sides so that you can show that that is the p at k plus 1 statement, so that it's true.